Okay, so hi everyone. So welcome back to this new video in this segmentary series. So today in this video we will be discussing this harder problem from Codeforces Div 1 round 225, and this problem is rated 2000. So before starting this problem, if you have not yet subscribed my channel, please consider subscribing because I'm already creating a lot of amazing content for you guys, and I have planned to upload more and more videos related to segmentary problems, including lazy propagation, segmentary beats, and other harder versions of the segmentary, right? So yes, if you have not yet subscribed, consider subscribing and share with your friends who need to watch these videos to gain confidence in this topic. So let us now come back to the problem. So the problem reads like this: Lahab likes trees very much. Recently he discovered an interesting tree named as propagating tree, right? So the name of the question is also propagating tree only. The tree consists of n nodes numbered from 1 to n, and each node I having an initial value of a of I. So the root of the tree is node 1. So node 1 is the root, and this tree has a special property, that is, when a value val is added to a value of node I, the value minus val is added to the values of all the children of node I. Note that when you add value minus val to the child of node I, you also add minus of minus val, that is plus val, to all children of the child of node I, and so on. Look at an example explanation to understand better that how it is working. So this tree supports two types of queries. So the first query is of this type. So we will be given two values, that is x and val, and what we have to do, we have to go to the node x of the tree, and in that node we have to add this value val, and when we will add this value to that node, we also have to add minus val, that is this, to the child of this node x, and then we also have to add plus val to the child of this node x, and so on. That is, we have to continue adding this value val in alternate fashion, right? So this is the first query, and this is the second query. And in the second query we will just be given an integer x, and we have to do nothing but we just have to print the current value of the node x. So in order to help Lahab understand the tree better, you must answer m queries of the preceding type. That is, we have to answer the queries of this type only. So in the input we will be given two integers, that is n and m, that can go up till 2 into 10 to the power 5, and the second line contains n integers, that is the initial value of the nodes of the tree. Obviously the tree is rooted at 1, right? And each of the next n minus 1 lines contains an integer vi and ui, that is representing an edge between the nodes ui and vi. So these n minus 1 lines will help us to form the tree, that is the given tree. And then in each of the next m lines contains a query in the format described above. That is, we will either be given this or we will either be given this. And if we are given this query, then we have to print the answer, that is print the current value of the node x. And for each query of the type 2, we have to print the answer to the query on a separate line. This is the problem given, and this is the given example here. So this is our input and this is the required output, and here is the explanation for this input. So let me zoom this a bit. So in this input we are given a total of 5 nodes and 5 queries, and for each of these 5 nodes we are also given the initial values like this, that is 1, 2, 1, 1 and 2, and then we are given n minus 1 lines, that is 4 lines. So each of these lines represents an edge between the two nodes, that is a bidirectional edge is present between 1 and 2. Similarly, a bidirectional edge is present between 1 and 3, and so on. Finally, we are given with this m lines of queries, that is total 5 queries, right? And each of these queries are either of the format 1 type or 2 type. So whenever a query will be of the 2 type, then we have to answer this query. So that's why, since there are total of 3 queries of the 2 type, we are also given 3 integers in the output. So this is the question: Let us now go to the blackboard and see how the output is coming for this given input. So let us now go to the blackboard. So this is the given example in the question, and in this question we are given a total of 5 queries like this. So the first 2 queries are of the type 1 and the remaining 3 queries are of the type 2, and this is also our given initial tree in which the node 1 is the root node, which initially has a value of 1. Similarly, these green values represent the initial values of each of the nodes in the tree. So the first node is having a value of 1, the second node is having a value of 2, the third node is having a value of 1, the fourth node is having a value of 1, and last, the fifth node is having a value of 2. So this is the initial condition of the tree. Let us apply each of these queries one by one. So in the very first query, it is of the type 1. What we have to do in the first query? So since it is of the type 1, in this query the value of x is 2 and the value of val is 3, right? So what does it mean? It means that we have to go to the second node of the tree. So in this tree, where is the second node located? So the second node is located at this part, right? So this is my second node, and in this node what we have to do? We have to add a value of plus 3. If I add a value of plus 3, then what will happen? See, I am adding a value of plus 3 to this node because it is instructed in the query to do. But if you have read the question, then by doing this, it is not enough. That is, we have to propagate this addition. So since we added a plus 3 to this second node, it also means that we have to again add a minus 3 to the child of this second node, just like this. And since these two nodes are the leaf nodes of the tree, that is, we cannot propagate these values any further, right? So it means that we will stop now at this point, and thus this query will end here. So in this way our first query will be done. Now let us move to the second query. So in the second query, it is also of the type 1, and in this the value of x is 1 and the value of val is 2, that is 1 comma 2. So since x is 1, it means that we have to go to the node 1 of the tree. So in this tree, where is node 1 located? It is located at the very top, that is the root node. This is the first node, and in this node we have to add a value of plus 2. So if I add a value of plus 2, so it will be this, right? But what we have to do next? We also have to add a value of minus 2 to the child of this first node. So I will write here a minus 2 for both of these childs. And since this node has not any childs further, so we will stop at this point. But since for this node it has two childs on its both sides, so it means that we further have to propagate this value. So that's why, since I added a value of minus 2 here, so it means that for these two nodes I have to add a value of plus 2 instead. That is, here plus 2 and here also plus 2. And now since it has not any childs further, so we will stop now. And in this way our second query will also be done. The first two queries of the type 1 is done. Let us now move to the third, fourth and fifth queries. So in the third query, it is of the type 2 and the value of x is 1. That is, we have to actually print the value of the node x, that is node 1. So in this tree, this is our node 1, right? What is the value of this node 1 currently? So it is equal to 1 plus 2. That is 3. So I can say that the answer to this query should be 3. Alright. Now this query is done. Let us now move to this query. So in this query we have to find the value for the node 2. So since this is our node 2 here, so we have to print its value. So its value is what? It is equal to 2 plus 3 minus 2. So these two will cancel out each other and only 3 will remain. So I can say that answer to this query should be 3. So I will write here 3 again. And now if I discuss the last query of this input, then it is 2 comma 4. That is, we have to find and print the value for the fourth node. So in this tree, the fourth node is located where? So the fourth node is located here, right? And what is the value of the fourth node here? So it is 1 minus 3 plus 2. So it is equal to nothing but minus 2 plus 2, that is 0. So it means that the output for this query should be 0. And therefore in the output we just have to print these three integers on a separate line, that is 3, 3 and 0. So this will be my output, right? And if you have looked in the question, then the output is 3, 3, 0 only, right? So it means that our output is definitely correct. So in this way, the queries will be performed one by one, as I just told you. So I am sure that you must have understood the question and how the queries are being implemented in this tree one by one, and how the outputs are coming for each of the second queries. So before coming to the approach to solve this problem, there are few things that you must know beforehand, right? So let me discuss one of those things here. I will now discuss the concept of Euler tour. So let us now understand what is Euler tour and how it works, and why I am discussing this concept here, because it will be used in this problem. So let us now go and understand the concept of Euler tour. So what is Euler tour? So Euler tour is nothing but a technique we generally use in tree based problems, in which we represent the given tree into an array, right? So this is Euler tool. So we represent a given tree into an array. So what does it mean actually? Let me tell you. So this was our given tree, right? And these are the initial values present on the tree nodes, right? So now, as I just said you, that what is Euler tool? In Euler tool, we represent a given tree into a form of array. And why we do this? Because it is generally more easier for us to make operations on an array rather than doing it directly on the tree. For example, suppose you are being asked to find the GCD value of each and every node present in the subtree of 2. So you know that you cannot directly start from here. So it will be a little difficult for you to do this operation directly for this subtree. Apart from GCD, you can be asked anything to do, like the sum of this part, or the minimum, or the maximum, or any other operation, right? So in that case, it is little difficult to do it directly on the given subtree, right? So that's why we try to represent the given tree into a form of array, because after doing these many lectures on the segment tree, we know that it is relatively easier for us to calculate the minimum or the maximum or the GCD or any value in an array in a certain range using a segment tree, right? So that's why we try to represent the given tree into a form of array, and once this is possible, we can calculate any value related to a subtree, and I will show you how. Since I told you that this tree will be represented in the form of an array, so what will be the size of this array? I will discuss a particular type of Euler tour in which each node of the tree is visited exactly twice, right? And since I will be using one based indexing here, so that's why, since the total number of nodes given in the question is n, so I will take the size of my array as 2n plus 1, right? So if I write the array here, so this will be my array here. So this is my Euler tour array, right? And since I will be using one based indexing here only, so that's why this 0th index will be of no use for us. We will only start from the first index. So what we do in Euler tour actually is, so we will start from the root node here, and first we will travel to the left part, and then we will travel to the right part. And the first time we enter the node, we write its value in this array, right? Similarly, the last time we enter this node, that is the second time, that is the outgoing time, we again write its value in this array. So for this tree, if I start from this root node, then it has a value of 1 here, right? So that's why I will write here 1. And now I will move to the left part, and since I am entering the second node for the first time, which has a value of 2, so I will write here 2. Similarly, as I move to the left part again, I will reach the fourth node for the first time, which has a value of 1. So I will write here 1. And now what will happen? Since I cannot go here any further on both the sides, so I will return back, that is I will backtrack. So it means that I am now leaving the fourth node, and since I am leaving the fourth node and I will not return to this fourth node again in the future, so it means that I again have to write its value in this array. That's why I will write 1 again here. And now I will be standing at this second node. But since I have not yet explored this part, so it means that now I will be standing at this node. And since I have reached this node for the first time, which has a value of 2, so I will write here 2. So this will be 2. And now again, I will backtrack, right? That is, I will not return to this part again. So since I am returning back, which has a value of 2 here, so I will again write 2 here. So 2. And now I will be standing at this node. So since I am standing at this node and I will never in future return to this second node. So it means that I am going out of this node. So since it has a value of 2, so I will directly write here 2. So it will be 2. And now I will be standing here again. And since I have completely explored the left part, but I have not yet explored the right part, so I will now go to the right part. So now I will come to this node. So since I am coming it for the very first time, so I will write this one here. So this will be 1. And now since I can't go any further, so I will backtrack. So since I am backtracking and I will not reach this node again, so it means that I have to write its value again in this array. And now after backtracking, I am finally standing at the root node. And since I have explored both the left and the right parts here, I will finally backtrack like this. That is, I will finally leave this first node. So since at the very first time I entered this node here and now I am leaving this node, it means that I again have to write its value here. So I will again write 1 here. And I think I have took one extra side, so let me erase this. So this will be the status of my array after completing the Euler tour. And obviously this array is of the size 2n plus 1 only. That is 2 into 5 plus 1, that is 11. That is from 0 to 10. Right, so 0 to 10. So this is my Euler tour array. So now how this array will benefit us now? So now someone if asks you to find the sum for the subtree of this node 2, that is this tree, then how can you answer the same thing using this array now? So now how will you answer this question, that is the subtree sum for the second node, and you have to answer this question using this array now only. So since we know that we entered this second node here, right, let me mark it. So we entered this second node here and also we exited this second node where? So we exited this second node at this point, that is here. So it means that whatever node values are present in this range, it will only comprise of those node values that are present in this subtree, that is the subtree of 2. You can look also. So these two values represent the second value for this node, which is this 2. Similarly, these two values represent this value. And similarly, these two ones value represent this value. So each and every node present in the subtree of 2 is present in this range twice, right? So now if someone asks you to find the subtree sum of this subtree, that is the second node, so it should be equal to 2 plus 1 plus 2, that is 5. And if you also took the range sum of this range, so it will be equal to what? So it will be equal to 10, that is 2 plus 1 plus 1, that is 4, plus 2 6, plus 2 8, plus 2 10. And why this happened? Because each and every node was coming twice, so that's why the values also got added twice. So whatever the range sum we got here, that is 10, just divide it by 2. So what we will get? We'll get actually the subtree sum, which is of this subtree. So in this way, this Euler tour array can help us in many ways in order to do the subtree operations for a given tree. So now we know the use of this Euler tour array here. So we know this now. But how will you know that for this second node we entered at this index and for the second node we left it at this index? How will you know this? In order to solve this problem, that is to find the entry and the exit points in this array for a particular node, we use another two arrays. So the first array that I will use will be used in order to determine the entry time for a particular node, right? And I will name it as in time, let's say. But instead of holding the initial values, what does this array will hold? It will actually comprise of the entry time for each and every node. So if I draw it here, so now since I have filled my Euler tour array here like this, and now I want to determine the entry time and the out time for a particular given node x, right? So how can we do this? So it is very simple actually. So what I will say is, when I had started from the root node, I will actually increase my timer by 1 every time we visit another node. So initially our timer value will be equal to 1, right? So when we are present at this node, that is the first node, so I will say here that for this first node here, since I am present at the first node here, so I will say that the value that this array will contain now will be equal to 1, that is the timer value will be equal to 1. And now I will move to the left part, and now I will be standing at the second node, and since I am standing at the second node, so I will say here that in this second index the value of timer will get increased by 1. So since it was 1 before, so now it will be equal to 2. So it means that this value will be equal to 2 now. So you can imagine it something like, we are present at this node at t equal to 1, and then we are present at the second node at t equal to 2, and then we are present at this fourth node at t equal to 3, just like this. So that's why, since from this node I will move to this part here, that is the fourth node, which is located at this index. So that's why I will write here 3 now, and now my timer value will increase to 4. So what does this array is holding? This array is holding the initial time, that is the in time for each and every node. But since now for this node I have to also backtrack, that is in time is done here, but now I also have to fill the out time for this array, right? That is at what time I actually reverted back from this particular node. Similarly, at what time I will revert back from this particular node, and at what time I will revert back from this particular node. So since we also want to fill the out time in the same way as the in time, and this out time will help us in order to determine this index, that is the second time we left the particular node. So now we want to determine this index. So what is this index? This is my in time and this is my out time, right? So that's why we will also consider another array just like this in time, as I told you before. So this is my in time array and this is my out time array. When we wrote these three here, we were present at this node, right? So we started from the root node at t equal to 1. So we wrote here 1. Then we reached this second node at t equal to 2. So we wrote 2 here. And then we reached this fourth node at t equal to 3. So we wrote 3 here. But now since we are moving out of this fourth node and will not return back to it, and now we know that after writing this value here, the timer value is increased by 1. That is, the timer value is now equal to 4. So that's why the out time for this fourth node in this out time array here will be equal to 4. So it will be 4 here. And now I will be present at this node. So since I am entering this node for the first time, so I will write here in this in time array that its value will be equal to 5, because every time the timer will increase by 1. And now since I have to leave this fifth node here, so that's why in this out time array at this index I will again write the value of increased timer. So it will be 6 now. And now after exploring both these left and right parts, I will be standing at this node again. And since I have to again go from this node to the upper side and I will not return to this node again, that is, I am going out of this node. So what will be the out time of this second node here? So it will be 7 now, because every time the timer value is getting increased by 1. You can imagine it like a tickling clock. And now once the left part is explored completely, I will move to this part. So now I'll be entering this node for the first time, that is the third node. So we have to fill this point here. So it will be equal to 8, right? And now since I have to leave this node, that is I have to get out of this node here just like this. So I have to fill the out time in this array here at this index. So it will be equal to what? It will be equal to 9. And then finally after doing this, I'll be standing at this node again, and since I have explored both the parts, it means that I have to go out of this first node ultimately. So since I am going out of this node, it means that I have to fill this value here. So it will be equal to what? It will be equal to 10, because before my timer value was 9. So as you can see that only these much indexes are getting used and not these much, right? So it is not necessary to take the size of these two arrays, that is the size of in time and out time array, as the same size as of this Euler tour array, right? So this is not necessary. You can just take it of the size as n plus 1. So since my n was 5 here, so 5 plus 1 6, so that's why I am able to access the 0 to 5th index easily. So this will be sufficient. You don't need to take the whole size, right? So now let us come back to the problem what we are doing. So as I was telling you before, that since we wanted the subtree sum of the second node here, so we wanted to determine this left index and right index, right? That is the entry time for the second node and the out time for the second node. So if you look here in the in time array, then in this in time array, the value of this second node is equal to 2. So it means that in this second node we entered it at t equal to 2, that is this index. So in this way we will be able to determine this left index in this Euler tour array. And similarly, since we want to also determine the out time for the second node, so we will look at the second node here, that is the second index, which has a value of 7. So since it has a value of 7, it means that we exited this second node at t equal to 7. So if you look in the 7 index in this array, which is located here, so in this way I will be able to determine the right index of this second node in this Euler tour array. So that's why these two arrays, that is the in time and out time array, are helping us with nothing but just to determine the left and the right index in this Euler tour array. And once we are able to determine this, that is the left index and the right index in this Euler tour array, we just have to take that particular range and perform whatever given operation the question wants us to perform. So as I told you before only, that if I want the subtree sum here, so just take the subtree sum of this range and just divide it by 2, right? So since every node was coming twice in this range, so that's why I'm dividing it by 2. And whatever we will get will be the subtree sum for this particular subtree. Similarly, you can also be asked to perform any other operation in this subtree range, right? So this is the whole concept of Euler tour as I just described you with the help of these three arrays, and I'm very sure that you must have understood it because I could not have explained it any better. This is the simplest explanation of Euler tour that anyone can give you with these pretty visuals. And since this was the only given tree in the input also, so that's why these three will be used very soon. So I will not erase this. So let us now go back and see what the question was asking us. And if you have read the question correctly, then what is this first query is actually about? So it wants us to add a value to this node X, right? But actually we know that it is not about just this node X. Actually we have to do it for the whole subtree of this node X in alternate fashion, right? So since it wants us to add this value in alternate fashion for this whole subtree of this node X, so notice the word subtree. That's why I taught you this concept of Euler tour, right? Because now we know that whenever we are asked to perform a subtree operation particularly, then this Euler tour concept is very useful, because by using this Euler tour we can simply convert this given tree into an array and just perform the range query as required. So now what I am saying is, if the question had asked us to not do it in alternate fashion, that is just add these two value, that is plus 2, to each and every node of this subtree here, that is plus 2 here, plus 2 here, plus 2 here, plus 2 here, and plus 2 here. So if the question had asked to do this, then what we could have done in that case? Then it would be a very simple task actually. So since we knew in that case that the entry time for this one was 1 and the out time for this one was 10. So in that case we will have just took this range, that is from 1 to 10, and simply increased each of these values by a plus 2. So I would have said that t.update from 1 to 10 I want to increase by a value of +2. So it would be a very simple task. But now the question don't want us to actually increase each and every value in a particular range by a common value, right? So for some indexes it wants us to increase by a plus value, and for some indexes it wants us to increase by a minus value. So this is why this problem is a little good problem other than a normal Euler problem, right? If you have solved these three problems before, and I also made a video on a question named as Xenia and bit operations. So in this question also we were asked a similar thing, not actually similar, but yeah. If you remember, then in this question for some of the levels of the segment tree we were asked to calculate the XOR value, and for other levels we were asked to calculate the bitwise XOR value, right? So what we used to do in that case, we actually used to take the help of the height of the nodes, and by using the height of those nodes we are able to determine whether to perform either the bitwise or the bitwise XOR for a given range or a given level, right? So that's why whenever we will be asked to do something alternately, because in that question also we were asked to do this, that is OR, then XOR, then OR, then XOR, and continuously like this, that is in alternate fashion. So whenever we are asked to do these things in an alternate fashion in a tree, then the height of these nodes play a very important role, keep this in mind, right? Or the level of these nodes, right? So that's why now what I will do here now is I will calculate the height for each of these nodes. So for that let us draw an array here. So now let us start filling the array values one by one, that is the height of each of these nodes. So since we know that, we will start from the root node. So let's say that the height of this root node is actually 0, and then the height of the child of this root node is 1, and then the height of the child of this further nodes is 2. So 0, 1 and 2. So this is my level array, right? I hope you got this. So once we have calculated the level for each and every node, so this level array can help us now in order to determine whether to add a value of +2 to a particular level or a value of -2 to a particular level. So in order to explain you this concept using the level array even more better, let me draw two figures. So now, since these were our given queries, right? So what now I'm saying is, let us actually perform these queries one by one, and I will perform it on both the sides, that is this side and this side. So in this side, as I have written that what our eyes will see, so what I will do in this side is the same thing as the question has asked us to do. So if the question will ask us to add a value of +2 to this node and -2 to this node and again a +2 to this nodes, then I will just do the same thing without any change. But our algorithm will not be able to do this directly, right? So whatever the algorithm will do with this tree, I will write here. So that's why I have drawn two figures here. So let us do it one by one. So since in the first query it wants us to add a value of +3 to the node 2, what I will do now, I will add a value of +3 to this node here, just as being instructed in the query to do. And since I have added a value of +3 to this node, it means that in the direct child of this 2 node, I have to add a value of -3. And I will stop at this point because there are no further childs of both of these nodes, right? So we ultimately want to do these things. That is, ultimately after performing these operations, I want to have a value of +5 on this node, I want to have a value of -2 on this node, and I want to have a value of -1 on this node, right? If I want to do the same thing with this side, then I won't do it directly. So what do I mean by this is, as we have already calculated the levels for each of these nodes, that is 0, 1, 2. So let me write that here only. So we know that this is our 0th level, this is my first level, and this is my second level, right? And obviously this first level is my odd level, and this 0 and 2 levels are my even level. And before actually seeing how the algorithm will work for this side, I want to tell you one more thing. So since this was our Euler tour array, right? So this was our Euler tour array, but now what I am telling you to do instead is, for the even level nodes, that is, since here this 0th level and this second level are the even levels, so now in this Euler tour array, nodes we encounter on the even level, so whatever values they will possess, I will directly write those values in that Euler tour array, right? But for this odd level nodes, that is here the second node and the third node, instead of putting this 2 and 1 in the Euler tour array, I will actually put -2 and -1, right? So now what I'm saying you to do is, instead of putting this 2 and 2 here, that is the value for the second nodes which was present at an odd level as of now, I will put a -2 here actually. Similarly for this third node also, I will put -1 instead of +1. So since the third node is represented by these two indexes, so that's why I will store here -1 instead of +1. And you will very soon realize how this technique or little modification will help us now. So this is the Euler tour array that we will construct initially based on the level of the nodes. So this is the current status of my Euler tour, right? So whatever Euler tour we will construct, it will be this only, right? So whatever nodes are present at the odd level will actually hold the negative value of the original values. And since the odd level nodes have a negative value of their original value, so that's why here instead of this +2 it will be -2, and similarly instead of this +1 I will write here -1. So now since I want to perform an operation on this subtree of second node, so we know that for the second node this is the required range. So whatever operation I will apply, I will only apply to this particular range. So this is our left index and this is our right index, right? So that's why I will say here that t.update from the left index to the right index. So whatever operation I will perform, it will only be performed in this range. So now what technique I am telling you to apply is, since in the question it wanted us to actually add +3 here and -3 on the childs, but now I am telling you to do instead what is, since this is an odd level and it wants us to add a value of +3 here, but now instead of adding this +3, just add a -3, right? So if I add -3 here, that is on the odd level x, so I will get what? I will actually get this. So here, so in order to do this, I will actually pass -3 here, right? So when I will pass -3 here, it will actually add -3 in this whole range. It means that it will actually add this -3 in this node also and in this node also. I actually did an opposite thing. Since the question wanted us to add a value of +3 on this odd level node, but now what I did was, instead of adding this +3, I added a value of -3 on this odd level node. I did the same thing actually for this entire subtree and not just for this node. So I added -3 here also, -3 here also, and -3 here also. And now if you calculate actually, then actually after performing this query, I wanted it to have a value of 5, I wanted this to have a value of -2, and I wanted this to have a value of -1. Alright, and now if you calculate it for this subtree here, that is after performing this operation that I just told you, then it will be equal to what? It will be equal to -5, it will be equal to -2, and it will be equal to -1. So if you have noticed, then here we wanted to have a value of -2 and we are getting here a value of -2. Similarly, here we wanted a value of -1 and here we are getting a value of -1. But here we wanted a value of +5. But here instead of this +5 we are getting -5. So out of this -5 I want to have a value of this 5, that is the actual value. So how can I get this 5 from this -5? Just take the negative of what is stored here. So minus of -5 is +5 only, which is our required answer for this node, right? So that's why this trick is helping us in order to actually determine the value for each and every node after the operation. So that's why I told you that whenever the level of the given xth node for a query is odd, then instead of adding this given val in the query directly in the whole range, I will actually add a negative value, right? And since for the odd levels I have initially stored the negative values instead of the original positive values, So they will cancel out each other somehow, right? And even if they don't do so, I will actually take the negative of whatever the result will be stored at that particular node, and that will always give us the correct answer. And for the even level nodes here, whatever the answer will be stored here will actually match what we want. So we don't have to do anything for the even level nodes. It will always contain the right answer. But for the odd level nodes, I have to actually print or return the negative of what is stored. So that's why if it is an odd level, then in this range, in the Euler tour array, I will increase each and every node by a negative value. And I just told you how can we use this simple thing in order to determine the value of each and every node in this subtree. That is the correct value. For the even levels, it will print the same value. But for the odd levels, we have to take the negative of what is stored, right? And if this is not the case, that is, the level of x is not odd, that is, it is even. So if this is even, then what I will say? I will say here that again I have to update this whole range only from left to right, but instead of adding -3 in this whole range, I will just add a +3 here. That is the opposite. Since this query has been performed and now I want to perform this query, so as you can see that in this query, I want to add a value of +2 on the first node. That is +2 here, and if I add a value of +2, I want to add a value of -2 here and again +2 here. So this is the actual thing that we want to compute. Then if I write here, then I actually want to add a value of +2 on the first node and then -2 here and then again +2 here, right? So what this is equal to? It should be equal to 3 minus 1, 3 minus 2 plus 2 0 and -1 plus 2 1, right? So the actual values on these nodes that we should get after performing the second query are these, right? And if I try to do the same thing here in this side, but using the logic that I just told you. So currently my x is 1 and my val is 2. So my x is 1 and my val is 2. And since my x is 1, so what is the level of 1? That is this level. So it is 0, and we know that 0 is an even level. And if it is even level, it means that we have to execute this statement. That is, I will first find the left and the right index for the first node using the Euler tool. If we look in the in time and out time array for the first node, then here it is equal to 1 and here it is equal to 10. That is, in this Euler tool array, in the first index, this will be my left index for the first node, and this will be my right index for the first node. So whatever operation we want to perform now, I want to perform in this range, right? We have got our left and right part, and as I have told you already, that if it is even level, then instead of adding -3 as before, I will just add +3 as given in the question or the query to do. So I will just add +3 in this whole range. So what will happen if I add this +3 here in this whole range? In each and every subtree of this first node, I will add +3. So let us see what will happen after doing this. And sorry, this is not 3 actually. It is now 2 for the second query. So it was 3 for the first query and it is 2 for the second query, as you can see. So it was 3 for the first query and now it is 2 instead of this 3. Now I want to add each and every value in this range by +2. So let's see what will happen if I do this. So if I add a +2 to each and every value in this subtree like this, so what value we will get? Let's see. I will add +2 here, here also, here also, here also, and here also. And if I sum this, then this will be equal to 3, this will be equal to 1, this will be equal to -3, this will be equal to 0, and this will be equal to 1. After performing this operation using this logic that I told you, I will get this tree, right? Now if you compare both of these trees, then actually after performing the second query, I wanted my tree to look like this. That is, I wanted each and every node to possess these values, right? But after performing the logic that I told you here, I am actually getting this tree. If I compare the node values one by one, then let us start from the root node only. So since in this tree for the first node, I wanted it to have a value of 3. And if you look in this tree also, then for the first node, it is 3 only. So it means that we are getting correct value for the first node. Similarly, if you look for the fourth and fifth node here, so for the fourth and fifth node, I wanted it to have a value of 0 and 1. And also if you look in this tree, then it is giving us 0 and 1, which is correct. And if you look for the second and the third node, then we wanted 3 and minus 1. 3 and minus 1. But instead of this 3 and minus 1, in this tree we are getting minus 3 and 1. Right? That is, we wanted 3 and minus 1. But we are getting minus 3 and 1. How can we get this 3 and minus 1 from this minus 3 and 1? Just take the negative of both of these values. So if I take the negative, I will get 3 and minus 1, which is our actual answer. So that's why this leveling concept is helping us in actually order to determine the correct value that should be present in the node after performing the query. Right. So if I write here, then if I am performing this else operation, that is this operation, then after performing this query, the even level nodes will give me the correct answer. But for the odd level nodes, I have to take the negative, and then only it will give me the correct answer for that particular node. Similarly, for this if condition, it will give me the correct value for the even node. But for the odd condition, I actually have to take the negative, and then only it will give me the correct value for that particular node. Right? That's why whatever answer these queries will return, I will check if the level of this xth node is even or odd. So if it is odd, then I will take the negative. Otherwise, if it is even, it means that it will hold the correct values, just as we saw for these two even levels. So it will always hold the correct values, but for the odd levels, it will hold the negative of what value should be present. So I will just take the negative. And if we move forward in the query, so we are done with these two queries, and now we want to answer these three queries. So for this query, it is 2, 1. That is, I want to find the value of the first node. So if we look in this first node here, then it is equal to 3. And here also if you look, then it is equal to 3 only. We will just check what is the level of this first node. So if the level is odd, we will take the negative. Otherwise, we will take whatever the value it is present already in that node. Right? So since for this first node, that is this node, the level is 0, which is even. So it means that whatever value it is containing here will match the actual value that should be present. So I will just print that value, which is 3 here. So I will get 3 for this query. And now if I look for this query, then here x is equal to 2. That is, I have to find the value for the second node, which should be 3 here. But if I look in this tree, then here instead of this 3, it is minus 3. And why this happened? Because this 2 is present at an odd level. So I will check if this 2 is present at an odd or an even level. So since this 2 is here present at an odd level, so I will just take the negative of whatever value it is holding. So since it is holding minus 3, so I will take the minus of minus 3, which is plus 3, and this will be my correct value here. So in this way, I will perform this query. And now if I move forward and perform this last query, so for this query, I want to find the value present at the fourth node. So here if you look, then at the fourth node, the value that should be present should be 0. But if you look in this part of the tree, it is holding 0. It means that whatever it is holding is true, and we don't have to change this. And why this happened? Because whatever the level of this 4 has, the level of this 4 actually is even. And it is true because the level of this 4 is 2, which is even. And if it is even, then it means that whatever value it is containing will actually match whatever value it should hold. Right? In this way, this query is also done. So this will be my whole approach for this given question. So I think I have explained you this problem in very detailed manner. Like first we saw what this question actually wanted us to calculate, and then I told you the concept of Euler tour, right, in very detail, how it uses the in time and out time in order to find the left and the right index for a given node, and what does this Euler tour actually holds, right. And I told you in this question, instead of directly holding the original values, I will construct this Euler tour. That is, for the odd level, I will actually store the negative values of what it should hold, right? And once I have constructed this Euler tour initially, I also told you to calculate the level of each and every nodes, because this level of nodes will actually help us to determine what update function we should apply in the query. So if the level of the current x, was an odd level, it means that I wanted to update the whole range by a negative value what is the query is asking us to pop. So if the query want us to add a value of plus val, then instead of this plus val I will add a value of minus val in this whole range, and whatever tree we will get, we saw that for the even level nodes we will get the correct value, but for the odd level nodes we will get the negative. So I'll just take the negative once again in order to get the correct value, right? Similarly, if this was not the case, that is the level of a given x node is even. So if it is even, then I will just update the whole range with the given val value. That is, increase the whole increase the whole left to right range by this plus val, right? And after we do this, whatever tree we will get at the even level nodes, I will actually get the correct values every time. But for the odd level nodes, we will again get the negative value. So again we have to take the negative in order to get the positive values, and which is our correct answer, which is obvious from this side also. So this was the whole thing for this question. I hope you have understood this, and now I think it would be very better for us if we actually move to the coding part and actually code this up and then quickly submit it onto the platform to see if we are correct or not. So let us now go to the code editor and quickly code this up. And yes, if you're still watching the video and have understood everything till now, and if you're really enjoying the video and the series, please like this video and subscribe this channel, because as you can see it is taking a lot of efforts to create each and every single video, right? So yes, please consider subscribing the channel. And let us now go to the code editor and quickly code this up. So first we have to take the inputs of n and m. And then we have to take the input for the n integers, and I will store it in a vector, let's say as val. So let me declare this val here globally. And since the maximum value of n can go up till 2 into 10 to the power 5, so once the input for the n integers is done, what we will do next, I have to take the input for the tree, that is for the n minus 1 lines, right? So that's why for each line there will be two integers, that is u comma v. I have to draw a bidirectional edge between them, right? So for that, let me declare an adjacency list here. So it will be also of the same size, that is 25 plus 1. And I think this should not be a constant expression, right? So let us now direct the edges. So I will say here that g of u, I have to take the input for the m queries, right? That is from 0 to m minus 1, I will go. And for each of the query, I will first take the input of the type, right? So if it is of the type 1, then it means that I want to actually update the tree, right? So this is an update operation. But if this is not the case, then it means that the query is of the type 2. So it means that I have to actually answer the query. So I have to find the answer for this query. And then at last I will just return. But we know that before actually starting our query operations, we first have to construct the Euler tour, right? And we have to do it in one based only. So that's why I will declare my Euler tour array here, right? And initially, since I don't want to use the 0th index, so that's why I will hold some random value here, let's say minus 1. And now in order to construct the Euler tour, what we have to do, we have to use the in time and out time arrays, right? So that's why I will use here and declare here the two arrays, that is the in time, which will be of the size as this, right? And in the same way I also have to declare the out time array, which will also be of this size only. So once I have declared these two arrays here, I also have to declare the timer, I guess, right, which will increase by 1 every time. So this will be equal to 1 initially. And now once I have written this, I think I should start my Euler tour operation. So I will call the DFS for the Euler tour, that is the Euler DFS, and I will start from the root node obviously, right? What is the parent of the root node? So there is no parent for the root node, so that's why I will take minus 1 arbitrary value, right? So that's why I will take it as minus 1. Since I also have to store the level for each of these nodes, if you remember, right? So I also want to store the levels for each of these nodes, so that's why I will also use a level array here, which will be of this size only. So now I will pass the level for the initial root node. So what is the level? So it is 0 only, just as I told you in the explanation. So let us now write our Euler DFS function here. So I will say here that the level for this node will be equal to this d, right? And the in time for this node will be equal to this timer plus plus, because every time some timer value is stored in a node, it will get increased by 1. Also, the Euler tour array will hold this current node because it is getting visited for the first time. But as I told you that it will depend on two conditions. That is the level of the node. We have to check, right? So if the level of the node here is actually odd, so if it is odd, then I told you that we will actually store the negative value of it, right? So if this is odd, then we will store the negative of whatever value is present in this node, that is this. And if this is not the case, then we will just store the positive value, just like this. And once this is done, I will start traversing the left and right parts. So I will traverse the adjacency list here one by one. I will check that if this child here, if it is not equal to the parent. So if this is not equal to the parent, because this is how we do a DFS in a tree, right? We don't use a visited array. So if this is not equal to parent, then I will again call the same Euler DFS here, and this time the parameters will be what? So the node will now be my child and the parent will be this node, and the depth will increase by 1. So this, and once I have written this, now this part will do the backtracking. So we know that during backtracking I have to fill the out time array. So the out time for this node will be what? It will be timer plus plus only, right? And since I am doing a backtrack, it means that I am leaving this node, right? That is, I am going out of this node. So in the Euler tour array, I also have to push this node again. This same thing here. So let me copy this. So this. And then finally I just have to return. So in this way our Euler tour will be constructed, and once this Euler DFS is calculated, so now I will declare a segment tree, right? And this segment tree will be constructed on this Euler tour array only, right? So this, and let me now copy my standard segment tree template here. So this is my standard segment tree template here. As you can see, this is a lazy propagation template, obviously, because I have to update the whole range, right? So the standard one will not work. I am using the lazy one, right? So keep this in mind. So now as I have declared this segment tree here, let us now start our query operations one by one. So what I told you that for the type 1 query we will be given two things, that is the xth node and the val, right? So what we have to do here, we have to first find the left index and the right index in the Euler tour array for this xth node, that is the left index and the right index. And this left index is calculated in the in the in time array like this, and similarly the right index is calculated in the out time array like this. And once I have found the left index and the right index in the Euler tour array, what I told you to check, I told you to check if the level of this xth node is actually odd or even. So if this is odd, then if you look here, I told you that if this is odd, then I have to update the range like this, that is the negative of val. So if this is odd, then I will say t.update from this left index to this right index by a negative value of this val. And I just told you in the explanation very well why we did this. And if this is not the case, it means that the level is even. And if the level is even, I have to update the whole range, but by this plus val only and not minus 1. So in this way the first type of query will be performed, and in the second query type I have to answer. So how can we find the answer for the second type query? So in this I will just be given an x, right? If I want to find the value for the xth node here, let's say for this query I wanted to find the value of second node here, that is this node here, which should be 3 here, which was minus 3 here, right? So obviously since the operation was being performed on the Euler tour array, which was passed in the segment tree initially, so we know that for this second node present in this range, right? And whatever the value this left index will hold here for this second node will be the same value as this right index will hold for the second node, that is here minus 2 for both. And since I just want this minus 2 here, so that's why, how can I obtain this value? I can just do a range query, that is the query sum for this range, that is from 7 to 7, or the query range from 2 to 2. So this will give us what? It will give us the summation of this range. And what is this range summation equal to? It is equal to nothing but the value of that particular index that should be present after performing the first type queries, right? So that's why I will say here that the result that we should get will be equal to what? It will be equal to t dot query from the in time of x till the in time of x only. And you can also write it here from the out time of x till the out time of x, because both are containing the same thing only, right? So you can either write this or this, there is no problem. So once I get this, I will get the value as required, right? But I told you in the explanation that whenever we will answer the second query, for the even level nodes we will get the correct value, but for the odd level nodes we will get the negative actually, right? So that's why here we will check that if the level of this x is even or odd. So if this is odd, then we will do something, otherwise we will do something. So if this is even, then whatever result value we got is correct. So I will just print this, right? But if this is not the case, that is the level is odd. So whatever result we got is actually the negative of what we should get. So that's why I will multiply it, or rather just print it like this. And in this way I think the whole code will be written, right? So now if I run the code, let's see if it is giving correct outputs or not. So as you can see that we are getting the correct results, right? So now if I try to submit this solution on the Codeforces platform, let's see if this is giving accepted or not. So as you can see that the solution is accepted, right? And this is the code that we just wrote here. So the usual segment tree template for the lazy propagation, then this simple Euler tour concept here in order to construct the Euler tour array, and after this the query logic, that is when we have to multiply it by -1 and when we don't have to multiply it, and how this thing helped us in actually calculating the result that we wanted to calculate, right? So thank you so much for watching this video till this point, right? I really hope that you have got the concept in this problem and actually enjoyed this problem very much. And also I hope that you learned something new, that is for those who have not studied Euler tour before, you must have understood how this works under the hood here. And if you have not subscribed the channel yet, please consider subscribing, because it takes a lot of efforts to create every video here. And I have planned to actually upload more and more videos related to segment tree this month. And after this segment tree series, I have planned to actually start the dynamic programming series here, right? Which will be a lot better than you can imagine. So yeah, thank you so much for watching this video.